Hello, everybody. So we are going to continue what we were discussing before about the process variables, and we will go back to the flow sheet that we saw before. And we said before that the arrow represents a stream that contains component going from one unit to another, and that this and this are called blocks, and that's why we differentiated between blocks and streams. Now I want to ask a question here, and this is where I'm going to, or the answer to this question is going to be the introduction to the topic of today. We have here ethyl benzene reaction. So ethylene and benzene are fed into the reactor and converting into ethyl benzene. The ethylene and benzene are not totally consumed, which means that there are some of ethylene and benzene didn't go into the reaction and they came out as ethylene and benzene. Some reacted producing ethyl benzene, which came out as ethyl benzene. So this is understandable. Now when these three components in this stream are fed to this separator, we have stream in the top and stream in the bottom, and this stream, and this stream, the three of them have the same components. So the question is, what is the difference between these three streams? This is a very, very important question. What is the difference between these three streams? All of them have the three components, ethylene, benzene, and ethyl benzene, and it doesn't seem that there is something different from one to another. And the answer is that the difference is in the concentration or the composition. Composition means that I will have the three components here, the three components here, the three components here, but I will have here, I can say 30% of this stream is ethylene, 30% is benzene, and 40% is ethyl benzene. But here I will have only 5% ethyl benzene, and here I would have 90% ethyl benzene, for example. So you will have the same components, but the ratios of the three components are not the same. So this is what a separator does. It separates the components into streams with different compositions. So we need to understand how we can represent this concentration or this composition or these ratios of these components. How can we understand this, and how can we calculate these concentrations? So we call it concentration or composition, and the composition is the relative amount of a component in a mixture. This is how we define it. It's how much of this stream is component ethylene or benzene or ethyl benzene. The composition is, and this is important because this is a very general definition that we can apply on what we will cover in this course and other units or other variables that we are not covering here. So it says that the composition of a component in a mixture, so it has to be a mixture, of course, it's not a pure component, is represented by the amount of a component, the amount of the component divided by the sum of the amounts of all the components. And this is the general definition. Based on this, the composition can be represented as mass of the component. Let's say I'm talking about benzene in the mixture of benzene, ethylene, and ethyl benzene. So the concentration of or the composition of benzene can be the mass of benzene over the volume of the mixture. It can be the number of moles of benzene over the volume of the mixture. It can be the mass of benzene over the mass of the mixture. It can be the number of moles of benzene over the number of moles of the mixture. It can be the volume of benzene over the volume of the mixture. It can be different things. But the common thing between all these alternatives that I just mentioned is that it is something represent the quantity or the amount of the component divided by the total of all the components in the mixture. So this is how we define a composition. In this course we will deal with two units, which are the mass fraction and mole fraction. There are other units of representing the composition. There is a concentration which is molar concentration, which is mole per volume, sometimes called molarity. There is something called normality. There is molality. There are many things, but in this course, and all of them represent the concentration. This is the point that must be clear, that all of them represent the concentration, and each one of them is used based on the application. Some applications prefer to deal with the concentration as molarity. Some others deal with normality. So it depends on what is the application that you want and which is more suitable. In this course, we will be interested in the mass fraction and mole fraction. In the mass fraction and mole fraction, and I think the name is clear. It's mass fraction. It's mass of benzene over the total mass of all the components. This is what we mean by the mass fraction. It's mass of component divided by the total mass of all the components. The mole fraction, it's number of moles of the component divided by the total number of moles of all the components. So just to clarify, let's say we have a mixture of 4 components, A, B, C, D. These 4 components can be benzene, toluene, xylene, ethyl benzene, can be hydrogen, oxygen, nitrogen, carbon dioxide, can be any 4 components. And the masses of the components are Ma, Mb, Mc, and Md. And the number of moles of the components are Na, Nb, Nc, and Nd. So if I want to define the mass fraction and the mole fraction, the mass fraction is going to be mass of A divided by mass of A plus mass of B plus mass of C plus mass of D. So it's mass of A divided by the sum of all the masses, which can be represented this way. It's sigma Mi, which is the sum of the masses. The same for mole fraction. It's number of moles of A divided by Na, Nb, Nc, and Nd. So it's Na divided by the sum of the number of moles. So it's as simple as this. This is how we define the mass fraction and mole fraction. Of course, it has to be clear that mass fraction is given the symbol X and mole fraction is given the symbol Y. And this is something we will be using in this course throughout the whole course. The value of XA and YA would be between 0 and 1. So either there is no A, so Ma is 0, so it's 0 over the denominator is 0, or it's pure A, so it's Ma is equal to is the same here, and B, C, and D are zeros. So its maximum value is 1, its minimum value is 0. So it's going to be from 0 to 1. Sometimes we like to represent the concentration or the composition instead of a fraction to be a percentage. So in this case, the percentage is the mass fraction multiplied by 100%. So if the XA equals, let's say, 0.1, then it's 10%. If it's 0.25, it's 25%. The same for mole fraction. So it's Y multiplied by 100. So both are representing the same thing. So it's not something new. We will have one example here, which is going to be something good to start with. That we have a mixture that contains 4 components: oxygen, nitrogen, carbon dioxide, and methane. We know the number of moles of oxygen and number of moles of nitrogen, of carbon dioxide, and methane. So the given informations are the number of moles. And this is something that must be clear from the beginning, that we know the number of moles. And we want to calculate the compositions in terms of mole fractions and mass fractions. So since we have information about the amounts in number of moles, it's going to be easy to calculate the mole fraction. So the mole fraction is going to be the n over the total number of moles. So the total number of moles is 13 plus 46 plus 7 plus 4, so it's going to be 70. So the mole fraction, according to the definition, is the number of moles of each component, or the mole fraction of a component. It's equal to its number of moles divided by the total, which is 70. So what I'm doing is I divide 13 by 70, 46 by 70, 7 by 70, 4 by 70, and then I have the mole fractions. So these are the mole fractions. Very straightforward, very simple, no issues here. The little more time consuming thing is doing the mass fraction calculations, because according to the definition, the mass fraction is the mass over the total mass. I don't know any mass. but I can calculate the masses. Last video we saw how we can get the mass from the number of moles. So we can do this by adding two more steps. The first is finding the parameter that we will use to get the mass from the number of moles, which is the molecular weight. And then from the molecular weight we calculate the mass of each component, and then we calculate the mass fraction. So for the first step, to calculate the molecular weight, oxygen is 2 multiplied by the atomic weight of oxygen, which is 16, so it's 32 gram per gram moles. Nitrogen is 28 by 2, so 14 by 2, it's 28. Carbon dioxide is 12 plus 32, so it's 44. Methane is 12 plus 4, so it's 16. Now, based on these molecular weights, I can use N and M to calculate the mass, which is N multiplied by M. So it's 13 times 32, it's 46 times 28, it's 7 times 44, and 4 times 16. So these are the masses of the 4 components that we have, and we can calculate the total, which is the sum of all of them. So now I know the mass of each individual component, and I know the total mass. So from this I can calculate the mass fraction, which is M over M total. So I'll do this for the 4 components, and now I have mass over the total mass, which is the mass fraction. So this is simply how we can do this. Given that, and this is again given that I know the number of moles of all the components. So this is a very important point that must be clear. One thing that sometimes makes things easy is to put the results in the form of table. So in this table we have rows, and for each row we have one of the components: oxygen, nitrogen, carbon dioxide, methane, and one for the total. And here I have columns: one for molecular weight, one for the molar flow rate. So what is in black is the given information. All the cells in red are the calculated parameters. So here the mole fractions are calculated, the total is calculated, the mass flow rate is calculated, and the mass fractions are also calculated. The good thing about the table format is that it summarizes everything, and it reduces the possibility of making mistakes in the calculation. So when you have each component in a separate row, you're doing the calculations using the information in the same row. So I'm using 13 over 70, I'm using 32 times 13, so the possibility of using this cell instead of this is less than doing this in a normal way. So just to put everything in a general rule, the mass fraction is M over M total, which can be put in this form as Nm divided by the sum of Nms, and the same for mole fractions, N over N total, which can be put as M over Ma divided by sum over of M over Mi. So just a general rule that you can use in case that you have masses and you want to use them to calculate the mole fraction, or you have moles and want to calculate the mass fraction. And if you look at this equation and go back to the this equation and go back to the previous slide, you would see that this is this is the formula that we used. It's M multiplied by the number of moles multiplied by molecular weight divided by the sum of, which is this, the sum of all the number of moles multiplied by the corresponding molecular weight. So this is just a general rule, just to make it just to make it clear. These formulas are used in case we have the data available are masses or number of moles. Next time we will deal with another case when we have no quantities. Sometimes we deal with cases where we have no given information as quantities, but we know mass fractions or mole fractions, and we want to get the other. So this is what we are going to discuss next time, inshallah. So I'll see you then.